So let's look at an example then. So it won't surprise you to know we're looking at the iris data again, but this time we're not going to use the species labels. So in other words, we're just going to use the 4 numerical measurements: the sepal length, the sepal width, the petal length, the petal width. Okay. So we're not using the species label, and we're trying to find clusters within the data. Now, we know there are 3 kind of natural clusters corresponding to the species, but we're not given that. So we want to see here if we can find any groupings naturally, just by the distances between the data points themselves. So doing k-means clustering in R is very simple. We use the k-means command. Okay, so what I've done here is first just select the numerical columns, so columns 1 to 4 of the iris data set. I've called that iris 2. Then I've done something here called set.seed. And the reason for doing that, you'll see that a few times in this section, in this chapter, is because k-means is a random algorithm. If you run it multiple times, you get a different answer each time you run it. So in order to make it run the same each time, which is useful for me creating lecture notes and for you reproducing the example, okay, I've set what's called the random number generator seed here. So if you don't know what that means, don't worry about it. It's just a way to always get the same random numbers. Okay, so you wouldn't do this for your coursework or anything like that unless you want to, unless you're compiling something and you want it to be the same every time, but it's just useful here. Okay. So to do k-means clustering, it's very simple. You type k-means, the name of your data set, so iris 2 here. Then you need to give it k, the number of clusters. So that's, you have to enter that as this label centers here. So I said I want 3 centers. And then you can also specify how many times to run the algorithm. So remember I said you might get stuck in a local minima here, and you can try that out and see if you get a different answer each time. So one way to avoid getting stuck in a local minima is to start the algorithm many times. So I said do the algorithm 25 times here. So this one's very fast because it's only a small data set. And this is the output we get. First of all, we get the mean of each of our 3 clusters. Okay, so the mean here, a mean here, and a mean here. Okay, I don't know how that compares to the mean for each species. You could perhaps have a look. You also get reported the clustering vector. So observation 1 belongs to cluster 1, and so on, up to observation 150, which belongs to cluster 2. In this assignment. You then also get the within cluster sum of squares. Yep, so these are for each of the 3 clusters. And it tells you some other information. Okay, it tells you the ratio between cluster sum of squares, so the total cluster sum of squares. So we're explaining 88% of the variance here, essentially. Okay, so from this we can read off the cluster means, the encoder, this bit, delta here, okay, and so on. Now, there's lots of ways of visualizing these things in R, but we're going to use the factoextra package that I've used previously, and it's got this nice command here, fviz cluster, that creates a 2-dimensional plot here. So the first thing it does is project the data points using PCA into 2 dimensions, because remember there are 4-dimensional points here. Yeah, we've got sepal length and width, petal length and width, so we can't visualize in 4 dimensions very easily. So what it's done is projected them into 2 dimensions, and then it's plotted the clusters on top. So you can see we've got a cluster over here, cluster here, and a cluster here with some overlap. Now it's also plotted the cluster means for us. So that's the larger circle, the larger triangle, and the larger square. So this is the final step of our algorithms. Remember, the way it works is that we have an initial guess of the assignment. We then find the mean. Then we do the assignment. We find the mean. We do the assignment, and so on. So in this case, we know there really are 3 clusters in the data, and so we can compare the clusters found with the clusters from the species. Okay, so I've used this table command here to do that. So what that does, it tells me how many of the setosa flowers are in cluster 1, and cluster 2 and cluster 3, and you can see in this case all the Setosa flowers have ended up in cluster 1. For the versicolor flowers, we found that 48 of them have ended up in cluster 2, and 2 of them have ended up in cluster 3. Okay. And then for the Virginica flowers, we've got 14 of them in cluster 2 and 36 of them in cluster 3. So, as I said before, clustering is a unsupervised algorithm. It's not trying to do classification. We're not telling it the algorithms, they're the clusters here, but you can see it recover them naturally. So if we didn't know there were 3 species of iris here, if we did clustering, this would do a pretty good job of finding those 3 different clusters. But of course, in most problems, if you've just given a data set like this, you wouldn't know how many clusters to look for. So how do we choose K? How do we choose the number of clusters? Well, what we can do is try clustering with different values for K. So here I've done it with 2 clusters. And you can see, this is probably a local minima here, right? You've got these 3 points over here that look really like they should be assigned to this cluster, but for some reason the algorithm's got stuck there, okay? And this is a local minima. But I expect if we ran it again and with 2 clusters, we would find that these 3 points are assigned to this cluster. So you can see the local nature of the minimization here. This was 2 clusters, this was with 3 clusters, this was with 4, with 5, and so on. The question is, how do we choose between these plots? 2 clusters, there's obviously at least 2 clusters. Yeah, we can see that by eye. But is there evidence for 3? I'm not sure. Okay. So in general, what we find is if we choose K too large, when you think about choosing K equal to the number of data points, then each point is in its own cluster. Yeah? Each individual cluster essentially begins to represent a single data point if we let K be too large. If we let K be too small, we find points get lumped together when they should be clustered separately. So the best approach is to use domain knowledge. So in this example, in the iris example, we know there are 3 species. So we know we're looking for 3 different clusters. And in many examples, we will have a hypothesis. We want to test, are there 10 clusters here? Can we find 10 clusters or 7 clusters, whatever? So that's the best approach, is to use this prior information that we might have about how many clusters there are. But in some cases, we may have no idea at all about the number of clusters. We just want to see, do the data tell us anything about the right number of clusters? So the most common approach for doing this is known as the elbow method. And what we do in the elbow method is to look at the within cluster sum of squares, W, as the number of clusters changes. So we look at the within cluster sum of squares for 1 cluster, 2 clusters, up to the maximum number of clusters we're prepared to consider. So at most we could let it be n the number of data points, I guess, but that's silly. There's no clustering. Yeah. So we're going to look at W as a function of the number of clusters. So here there's a command for doing this, thankfully. In this factoextra package, it's fviz nv clust. And so what we get here is the within cluster sum of squares, the within cluster, so that's W on the y-axis, and here is the number of clusters on the x-axis. So you can see with 1 cluster, we've got a large sum of squares. With 2, it drops off, 3, it drops off more, and then it settles down. And so what we tend to do here is to look for the elbow. So the point at which we no longer have a fast decrease. So the thinking is, if we look at the difference between 2 of these W's, then if we've used K clusters, when really this K plus 1 clusters, moving from K to K plus 1 to see a big decrease in the within cluster spread. Okay, so there should be a big drop here on the axis. On the other hand, if we've got enough clusters already and we add 1 more cluster, then what we're going to do is take a genuine cluster and split it into 2. And the thinking is that shouldn't reduce the number, the W by much. Okay. So this isn't a very mathematical argument. This is kind of a hand-wavy heuristic argument, but that's all we get left with. That's all we can do really here in cluster analysis. Use these heuristic arguments for choosing the number of clusters. So in this case, definitely, there's a clear information here that having 2 clusters is definitely better than 1 cluster, and we can see that by eye, right? There's definitely 2 clusters at least. The question then is whether there's 2 or 3 clusters. There's still quite a big drop between 2 and 3 here. So having 3 clusters definitely improves things. Going from 3 to 4 clusters or 4 to 5, not so much. Okay, so looking at this plot here, this elbow plot, I would say we would pick either 2 or 3, and probably would go with 3 because we still get an improvement in the clustering by going from 2 clusters to 3 clusters. Yeah, but definitely not 4 or 5. Yeah. So that's how we use these elbow plots. We look for the kink and we find where the within cluster sum of squares ceases to decrease rapidly. Note that it must continue to decrease. Yeah? But because we are not using a global optimization scheme, because we can't check every possible combination, because we can only check some of them, we're using this greedy iterative approach, sometimes we'll find an increase here. So going from 9 to 10 clusters, it looks like there's a slight increase here. And that's just a quirk of getting stuck at a local minima. Okay, so there's some examples for you to try yourself on the computer tasks. Have a go at K-means clustering.